All right, let's get right into it. So we're going to be talking about 3D printing your own injection molds. And this is really like the best way to get mass production potential off your 3D printer because you're still maintaining the rapid speed of injection molding, but you're getting the molds at a much lower cost. So traditionally speaking, I think we all think about this when we're looking at injection molding, but it's a very fast way to produce plastic parts, and you're going to get these parts with very repeatable results, like dimensionally or like from a service quality standpoint. And as such, you're looking at very low cost per part. In addition to the fact that it's kind of a largely automated process. I mean, if you've ever been to an injection molding farm, if you will, you'll notice there's like a robot that tends to each machine so that when the mold machine opens up, the robot arm comes in, takes the part, and loads it into a bin or onto the next process. And so as such, I mean, like when you think about kind of a simplified product that's produced on injection mold, like a Lego brick, you can see this mold produced 120 million bricks before it had to be retired from service. And that's a lot of parts to be able to produce on a single product. And those plates, those bricks there, they cost like maybe a cent or less to produce. And so you have to produce that many parts in order to justify the price of the machine and of the tool itself. And so that kind of leads me into this fifth point, and that's that the injection mold tooling is expensive. So traditionally speaking, when it comes to injection mold making, you've got like 4 criteria that go into it. So you've got like the traditional manufacturing method, which is like CNC machining and EDM. Then you have to look at like the raw materials that go into making the mold itself. So you're talking about like a big chunk of steel billet that has to go and be machined out. And because it's subtractive, there's a lot of material that's kind of getting wasted away. Then you have to have skilled labor. So you have to have a machinist who understands programming and understands the machine and won't crash the tool head and can perform the maintenance on it and knows how to use the software that goes into it as well. And so when you add up all of these different categories, what you're looking at is like 4 to 8 week lead times. Okay, so like 1 to 2 months. And you're looking at prices, 4-figure prices up to 6-figure prices and above, and everything in between. So it's like, what if you have a situation where you need to produce injection molded parts, but you have very low volume, say 100 or 1,000 or 10,000 parts, and you're looking at it and you're not going to be able to justify the cost of that tool. Or let's say you are creating a proof of concept and the components of that concept need to be injection molded. They need to replicate the mass production environment. And that way you can perform testing and have it be, kind of as close to one-to-one as possible, and you can validate your part so your investors, will buy off on it. Or let's say we have a third option where you have a product and a process that is highly iterative, and you cannot just simply, go off and start making the tool because you need to continue to iterate the design and perfect it. Well, the answer to any of these 3 situations is going to be to print your molds. You probably could foresee where I was going with this. Now, I'd like to talk about a customer case study who had to deal with a very unique challenge.
In a world where you need to produce thousands of identical parts, and you only have 1 week, and the design hasn't even started.
Well, all drama aside, this is the case that Braskem encountered right on the onset of COVID-19. So they needed to produce like 8,000 to 10,000 of these mask straps that go on the back of the head, just keeps the straps off your ears. And they had to produce it for their team that was operating in all these locations around the world. And so initially they looked at, okay, well, let's look at printing each one on like a standard FDM printer. That way we know it's going to be low cost to produce. But the factor that they have to consider is time. It's going to be very time intensive to print all of these. So they were looking at 72 days, upwards of like 2.5 months. So they said, okay, well, let's consider injection molding. Let's consider CNCing out a mold to go into our injection mold machine, And as you might imagine, time was much more realistic, but the project cost goes back to what I was talking about earlier. You're looking at 10 to 15 grand. You're looking at a very expensive cost to manufacture these molds. And so they're like, okay, well that doesn't really make sense. And so they got the idea. They said, well, what if we could marry these two ideas? We got the 3D printing side, and we're looking at a very low cost, and we've got the injection mold side where we're looking at very short lead times. And so they said, let's bring these two ideas together. We have a Form 3 Plus in our office. Let's see if we can put it to good use. And that's exactly what they did. And what they found is the project time was only 3 days.
For 3 days? Yes! Exactly. For 3 days.
So it took 3 days to go from the very initial design straight into designing the mold, printing the mold, and then injection molding these mass straps off. So it was extremely quick, and that's the nature of printing. You're gonna get your design apart very quickly, and also very inexpensively. Looking at a price of less than $400. So they went with that last option, and this was kind of their setup here. So they use like a medium-sized injection mold machine. It's a Cincinnati Millicron RoboShot, and they printed their molds using high-temp resin. And they only had to print one half because these mass straps are flat, and the other half is just like a steel plate that abuts up against that high-temp resin mold. And the actual injection shot material is a low viscosity polypropylene. It's also called high melt flow. It's so low viscosity that it flows almost like water. And so these were some of the conditions that they found after fine-tuning this process. This is what they found. And what you'll notice is there on that bottom image, you can see that the average cycle time was 30 seconds. And anyone who's worked in injection molding for a while knows 30 seconds is kind of a long time for a cycle time. But the reason they had to go that route is because the mold is, it's made of plastic, right? It's not made out of metal. And as such, it's not able to conduct heat away as easily. And so there's a lot of heat retention there. And so they have to leave the part in the mold for a little bit longer. In fact, Formlabs even recommends taking some compressed air and using that just to help expedite the cooling process. But all said, Braskem was able to get, on average, 15 shots per mold. I think they were able to get up to 2,500 at one point, but typically, right around 1,500, what they were kind of seeing there. So with this and all in mind, let's talk about design for injection molding. Now, we're probably more familiar with design for injection molding with, CNC machining or subtractive manufacturing in mind. But with additive manufacturing in mind to produce the mold, there's a lot of carryover. There's a lot of similar design principles there. So let's start out with a few of these. So for instance, unsupported walls, ribs. These are the kind of things you need to consider in terms of filleting, in terms of distance between ribs, thicknesses and heights. Also, when it comes to injection molding, it's always recommended to have your wall thicknesses be as close to similar as possible all throughout. But that's not always possible. So if you need to adjust between one thickness down to another, you want to do it very gradually. And so that's kind of what you want to look at. You want to have that length there of that gradual slope just be at least 3 times the change in height between those two thicknesses there. Probably the most classic and well-known principle for injection mold design is draft angle. So you want to have a draft angle of at least 2 degrees. The higher you can go, so if you can go up to 3 or 5 degrees, the better, the easier it'll be to remove that part from the mold. The other thing is filleting your corners. So corners can be an area where you can retain a lot of heat stresses and you can have some quality issues result. So you want to fillet those corners as much as possible. This kind of goes back to what I mentioned earlier about consistent wall thicknesses. So kind of in that upper right, you can see you want to avoid having just a solid block of material. It's more advisable to have that block shelled out and aim for wall thicknesses of like 1 to 3 millimeters. And lastly, just two things to consider there with engraves and with emboss features. Now, this slide here is going to cover some design principles that are more in line with using additive manufacturing to produce the mold. So for Brascom's case, going back to that one again with the mass straps, so here we're looking at the front and back of the mold. And what you'll notice is the back of the mold kind of replicates the design of the actual mass straps themselves. And the reason that it's kind of been shelled and cored out like that is, for one, it's not using as much material, and for another, it's going to help conduct heat away, better than if it was just like a solid block on the back end. Another thing to consider is scaling the physical part itself. So in CAD, what you want to do is you want to, and obviously it heavily depends on the shop material, but say for that high flow or high temp flow, low viscosity polypropylene, you'd want to scale that by like 2%. So you have your mass strap in CAD, scale it up by 2%, and then do like kind of your Boolean cut operation to perform or actually build the mold itself. And that's just to counteract any shrinkage of the material post mold. Another thing to consider is if you have ejector pins modeled into your mold, what you want to do is you want to model the whole diameter for those pins to be size on size with the ejector pins themselves. That way, after you finish printing, you can just remount those holes, really control how much material you're removing. And so you're still able to move those pins in and out, but still able to maintain the seal when you actually go to mold that part. If you're using a unit die master for your mold, you want the mold surface to be flush with that die master. And on the topic of the die master, what you want to design into the mold is for the head of the bolt to be flush with the surface of the mold and be directed inward towards the die master, so that the head is on the mold side and the threads are directed back into the die master, just like that. So it's a little bit reverse from maybe what you're used to if you're using other materials. All right, so with that wrapped up, let's talk about the ideal Formlabs resins to use for your injection mold. So at number one, you want to look at rigid 10K. And if you don't have that, a worthy substitute is that high temp resin. And then down at the bottom, use Gray Pro kind of as a last resort. And the reason we order it in that way is because of parameters like heat deflection temperature and tensile modulus. So you want to be able to resist the high temperatures of the molten plastic, but also have that high tensile modulus so you can handle high pressures during the injection process. Now we had looked at, with Brascom's case, we looked at kind of that medium-sized injection mold machine, but there are smaller variations that you can use, such as these benchtop injection mold machines here. So they're a lot more cost effective. But the only thing you have to consider, one thing I'll draw your attention to is like the three on the left here. Those are a manual injection mold. So that's uses a lever process, and then the two on the right are pneumatic. But you can see that these are really kind of smaller. They don't really allow large molds to be fitted in there. So if you don't really have access to something like this, or access to a more expensive injection mold machine, then you can always use something like a syringe or use a gravity pour method. And this is actually what we did, and we're going to show our example here in just a moment. But in situations like these, you don't necessarily have to shell out the money for more expensive resins like that rigid 10K or the high temp resin, which are engineering grade resins. In situations like this, you can use some of the more standard Formlabs resins like what we have listed here: black, white, gray resins, which are like your traditional standard resins, but also your clear and your draft resins as well. And finally, I just want to discuss 6 possible molding processes that are available if you're using 3D printed molds. So over here in the top left, we talked a lot about injection molding, but you can also rely on casting. So we'll have it where you can print, say, in castable wax resin from Formlabs, you can print your master. And so we have a lot of jewelers who are doing this. So they'll print the master, they'll coat it in a very high temp resistant ceramic material, and then they can burn out that wax master, and now you have a cavity where you can pull in, molten metal. So those are available. You also have overmolding, where you can actually sit the actual physical part, which is in this case some kind of like earpiece. You can sit that into the mold, and then you can pour a flexible material over it, and it'll coat it. You can also do like a compression mold where you mix part A and part B of a putty, and you squeeze it into the cavity, and you use high pressure, like a vise, for instance, to squeeze that real tight and fill all the crevices of the cavity, and then you can just kind of scrape away any of the remnants that have exuded out through the parting line. Now, down here in the lower left, we're looking at thermo and vacuum forming. So here you can see we're making a case, kind of the top lid for a straight razor, and so that's where you can physically print your master, and then you can use that to then create your product from there. Silicone molding is like really basic. Again, kind of like what I was talking about with casting, or even the vacuum forming method here. You're actually printing the master, and then you're just pouring in silicone, and then removing the master once that silicone is cured, and that way you have the cavity there to be able to pour in whatever material you want. And lastly, at composite molding, down here in the lower right, our final one, that's again where you're kind of creating it's kind of a blend between creating the master and just creating just a basic mold, and that way you can overlay your fiber layup and epoxy over it and form it to that mold there. All right, so for our example, we wanted to dive a little bit deeper into the overmold concept. And so we have this robot end effector that you see here. So it's just one of 2 of these, and they bolt in to a robot arm, and they actuate and grip a product. Okay, so this is what we're dealing with here. And let's say the product line changes, and we need to suddenly have a softer gripping surface. And so that's what we wanted to do. We wanted to design an overmold so that we could kind of create a coating of like polyurethane, just a urethane resin over just the tip of this end effector. Okay? And so what we did is we ran through this, and the first thing was just to kind of create the overmold, kind of what the overmold was going to look like at the end of the day. So you can see it just fits in over there. It's about it's like 2 to 3 millimeters thick, and it just routes around the entirety of the tip of this gripper. And we use this to create this combine subtract operation. It's a Boolean cut is what it's called. Okay, so we created the lower half. So there's our lower half here. And we created our upper half as well that you see here. Now what I'm going to do is I'm going to just hide our gripper, and I'm going to hide the overmold itself just to show you some more details. This little platform that extends out, if I unhide this just very briefly, you can see that it just supports it. So when it's rested flat on the table, the end of this is not going to want to sag down and cause any issues. So I just put a little support beam out there. I'm just going to hide this, and I'm going to hide the top bit here. We can kind of dig in and see what we're looking at. Okay, probably the first thing you'll notice is all these little pips here, all these little dowels that extend out. And what this is doing is it's just centering this. You can see these come out, and I don't know, it's about it's less than half a mil gap here. It's like 0.2 millimeters spacing between all of these, and they just help center it inside, just prevents any kind of wiggling or anything. Okay, and if I just do like a cross-section view, I just pull this out. See here, you can see, this is a good view here. Here you can see how these pins right here support it on the bottom. Because remember, we got to fill this whole space with that resin material. Okay. The other thing I want to showcase, let me just hide this gripper here. If I go in and I just pull a section view from one of these other planes, what you'll notice here is this is our pour spout. So you can see how it's this view might be better here. You can see how it's just this spout that runs down, and it's just filling the bottom, and it's filling up from the bottom the entire cavity with this resin material. Now, if I were to go in and just show the top, I'm just going to hide the bottom. One thing you'll notice, I have all these portholes. Now, I already showed you where the pour spout was. These portholes here are called vent holes. And vent holes were particularly important in this area, right in here. Okay, because you can get a lot of air bubbles that can get trapped in here. So you need these vent holes here to just help purge the cavity of any air bubbles. And you can see I really got overzealous with this, particularly because we don't have a vacuum chamber, any way to degas the resin before pouring. Now finally, I think the last feature I just want to showcase, and it's easy to see here, I just have kind of two locating features that allow this to mate together and not swivel or pivot in any way, shape, or form. So that's what we're dealing with on the overmold. Now, we went ahead and printed the two halves of this overmold. As you can see here, we got the top section and the bottom section, and you can see how we kind of angled them just to help with printability. But the only problem that we ran into is when we tore the supports off and we went to fit the two halves together, you can see that we were having issues maintaining flat surfaces. So we were seeing some, kind of a wavy appearance, and we weren't seeing the two halves being flush fit together. And that was a mistake on my part, because I found out later, with the help of Formlabs and with the help of one or two other webinars, that when it comes to printing mold halves, you actually want to print them flat on the build plate. And so that's what this looks like right here. So here was our first iteration attempt. You can see how it's angled. Well, after Formlabs' recommendation, what we want to do is if I go over here to where we can orient our part, and I'll just select kind of our bounding box here. If I select it like this, just like that, see how it's flat on the build plate? And I'm just going to rotate this around just to something like that. See, now it's going to print much better. We're going to have flatter surfaces here, and we're going to be a lot more successful, and we'll be ready to print. So after the print job was done, we went and double checked the flatness. And so you can see we have kind of a lip there on the very bottom. That's just where in the initial layers, the laser will kind of oversaturate, overexpose the resin, and just really get a good adherence between the first couple layers in the build platform. So it kind of elephant foots out. But because of that surface not being a critical surface for this mold, it's not really a big deal. But it is a reason, one of the reasons why you want to be wary of printing directly on the build platform. But anyway, we checked the flatness of the surface. You can see right there on that table there, and everything was perfectly what we expected. And yeah, so definitely took Formlabs' advice there. And anyway, we went ahead and got prepped and ready to begin the overmolding process. So once the molds are finished, what you want to do is you want to just coat it with some mold release spray. Just want to coat both halves of it with that mold release spray there. That'll help demold. And then you just want to prep your surface. What I like to do is just take a bit of tin foil, kind of fold it up on itself there all around the edges. That way when you go to actually pour the resin, you're going to get some spills. It's not going to want to leak out and get all over your surface. The next step you want to do is you want to go in and you want to rubber band or use some kind of clamp to hold the two halves of the mold together. And as you can see, I am not holding back. I'm using all the rubber bands that I have available, really getting it super tight. And then I'm taking a bit of like a silicone putty. This is just silly putty that I have available. And what I'm doing, and this is a step that's not necessarily mandatory, but I'm just going through along the parting line and just sealing it, just an added step there. I'm going to show an example later where we actually designed a channel inside the mold that allows for a bead of that putty to be run through, so you don't have to do this step. Alright, so once that's all completed, you are ready to begin prepping your two-part resin mixture. And so what we used was the Vitaflex 60 product from Smooth-On. I've seen a lot of makers on YouTube use the Smooth-On products, and they've used them to great success. They're a high-quality product. They have a lot of different materials. So I was using one of their urethane compounds. So it'll produce a rubber-like product, and it fits. They have a shore hardness scale, so you know exactly kind of what you're getting into. But there, I just put the Part A mixture in. And the Part B that I have, since I've had this product for like 10 months, the Part B definitely has a limited shelf life. And it formed like a crust already on the top. So I have a little bit of like solids in there. But yeah, so I'm just pouring that mixture, trying to get them out to equal levels. The nice thing with Smooth-On is their products are mixed by weight or mixed by volume. So I'm just doing volume here, just trying to top it off, get it pretty even. And from there, I'm starting to mix. And what you really want to do is you want to get all around the sides, the edges, everything, get it really thoroughly mixed up to get ready to pour. But yeah, once it's all mixed up, we'll get right to it. And so now you can begin pouring. This is what this pouring process looks like. I will say that this mixture is like maybe a step under honey in terms of viscosity. And just because this mold is kind of a constricted environment, not a lot of surface area, relying on gravity to pour this resin in is not advised. I definitely would recommend a syringe. And as you can see, kind of towards the end of pouring this, I had to lay the paper towel over the pour spout and blow the resin down into the mold, which it's not pleasant. Syringe is such a better option. So yeah, word to wise there. I had to become the human syringe for this experiment, and I'll tell you what, my cheeks started to feel like Dizzy Gillespie's by the time I was done with this. One thing I did is once it was all filled up, so when I realized it was filled is when it starts coming out of the vent holes, the resin starts coming out of the vent holes. I just topped off the top. I just poured whatever I had left up on top of the that second half there, just to make sure that I had completely filled it. And at that point, you just have to let it cure. And after it cured over the weekend, we demolded it. Had to just cut away some material from the top of the mold and cut away the pour spout, but it was able to demold very easily. It didn't need any prying tools. And this was a finished product. So as I mentioned earlier, if you have a vacuum chamber, you definitely need to degas the resin before you pour it. Otherwise, you end up with these bubbles here. And you can tap on the obviously you can tap on the mold there as much as you want, but you're not going to be able to get all the bubbles out. So had some bubbles there on the top, despite all the vent holes I put in, but there was very, very few to none at all in terms of bubbles everywhere else. It was just on that top surface. The final thing I wanted to discuss was a mold that we printed on our Markforged printer. This was in response to a third-party vendor that was no longer in service for one of our customers, and as such, they had to manufacture these roller wheels at a very high cost. And so I kind of showed them how instead of going that route, they could use their Mark II they had in house to print these roller wheels, these roller molds, and then pour it with resin. So So with that in mind, this is what I designed. So you can see our vent holes. That's the pour spout right there. And if we just crack it open, there you can see we use that Vitaflex 60 material again. So there you can see the top half of the mold and some of the keyways we used. 2 circles and a little square block there to align the mold together. And yes, we got our flexible mold. There you can see, kind of as before, we had some issues with bubbles there. Again, got to get a degas chamber. But one thing I like to point out is notice that channel right there. That's where we actually laid that silly putty bead in there to make it so that it wouldn't, spill out everywhere. All right, well, that's all I got for you guys. Appreciate you chiming in and joining in on the webinar. There's our 3D printing support options. If you want to reach out to us, you got any questions, talk to us about what cool things you got printing. No matter what, that's how you can reach out to us, contact us, and we'd love to hear from you. But, yep, I'll hand it on over.